Good afternoon, everybody. Good afternoon, everybody. So today we have the pleasure to receive Yacine Mokhtari from the University of Franche-Comté. The talk is about some PDEs in the control theory. So Yacine, please.
Thank you very much, dear Yacine. I want to thank first of all the team of TSMS for the invitation. It's a great honor for me to give a talk in front of such audience. I wish the best for the continuation of this seminar in the future. Okay, so in this first part of my talk, I will give a brief introduction to control theory in both finite and infinite dimension. We will see that later on. Okay, so what is it about, control theory? Consider this system, differential system that might be infinite or finite dimensional system. It depends on F and the space where we study this system. And I will call throughout this talk, Yt, the solution of the system, will be the state or the output in some control box theory. And this function here, U, is the control. And we can find this control in under some notation in box, the input, the command, etc., etc. So what is the goal of this story? If we give any target state in suitable functional space, that will be precise later, and I give a control time t, can I find or control U such that the solution, this solution with this control, does exist such control such that my solution at this instant t equals to the target state. So I have differential system. I solve this differential system. The solution will depend on U and Y0. And I ask this question here, does exist a control such that my solution at this instant t, we call this time by control time, equals to this target state or the goal or the desired state? This is the main question of this theory. This first talk is divided into two parts. The first is the linear case, linear finite dimensional control systems. That means that we study ODEs, controllability of ODEs in finite dimensional system spaces. And the second one is controllability of PDEs, and we will see the difference between these two cases. Okay. Let us put ourselves in these settings here. I will consider this system S, which is finite dimensional system. A is a matrix of size n, a square matrix. This B is of size n times n, rows with n lines, and this control U belongs to L2 0T and with values in Lm. I mean by this writing that the U is a vector valued function U1 till UN, and each component is in L2 0T. Okay, and I ask the following question, the same question as before: for time t, for chosen time, or the control time, or the desired time also, and for Yt given target state at this time, can we find a control U in this space such that Yt or our solution to this system equals to this target state? Naturally, ask this question, why there would be here? We could just put Ut. I will answer this question in few slides. Okay, so we can observe that if we let M greater than n, that means that S is controlled with a large number of controls, and this is not interesting from point of view of applications, since we will apply a lot of force or too much force to control a few states, in other words, and it's not interesting. The same case if m equals to n, we have the same number of controls as the states, and this is, we see that this similar as first case. The most interesting case is when the number of controls is less than the number of states. That means that we can control or as the question of controllability, if we do we can control the system as by one control, for instance. All the states are controlled by one control, and this is very interesting from point of view of applications. Okay, to go further, we can solve system as this just a differential system. I will call you that y prime equal ay plus f, and this initial state. Then the solution of the system is given by this formula, this the second member f, and we are done. This Jarmisch formula. And if we differentiate this yt, we fall into this formula with f is bu. And throughout this talk, I will call, I have to write that. I will call this a quantity here, this integral by LTU. And just a remark, the exponential of a matrix is given by this formula is a Taylor series, and it is always convergent and zero t. So the controllability problem reads as the following: we should find u such that at this instant t, I will replace this t here, and here, and here. This operator LT equals to yt, the target state, minus this state. Why that? Because if we ask the question of controllability, then if we replace this t here, this must equal the target state, and I move this to the left or to the right, and we obtain this formula here. So this controllability question is equivalent to the surjectivity of the operator LT from L2 0t with vector valued in Lm to Lm. If we can prove that this operator is onto, then we are done. So the whole controllability question is equivalent to the surjectivity of this LT operator. If we control our system with a large number of controls or with the same number of controls, then we can find an explicit formula for the control. For instance, if we assume that the rank of B of the matrix control is larger than n, then if we let U, our control, if we let it like that, and I plug it in this formula, LTU equals to the rest, sorry, the equation was LT equals to yt, the target state, minus exponential t anyway 0. If we plug this control, then we find that it satisfies this equation, and therefore it is a solution to this to our controllability question. This BR here represent the right inverse of the matrix B. Since the rank of B is greater than n, we know that B is a surjective matrix if only if there exists a right inverse to this matrix. If n equals to m, then the same thing happens. And here, if we assume that B is invertible, that means that we control each component with one control. Then we control everybody. Then this control is also a solution to our problem, and we are done. We control it at any time t larger than 0. So the main problem here is the case when the number of controls is less than the state. We cannot assume that the rank B is larger than n or equals to n, since our matrix has more line than rows, and we cannot proceed like that, this way. To get more clear idea, let me consider this.
Yacine, sorry, can I interrupt you? Sorry.
Yeah, yes.
Can you please go back? I didn't get it. So what is BR and what is B minus 1 in your expressions here?
Okay, this BR is the right inverse of B. If we assume that the rank of B is larger than n, then it is onto this matrix, and therefore, if and only if there exists a right matrix to right inverse to this matrix. Okay. To get a more clear idea about the problem with less number of controls, let me take n equals to who, So the number of equations equals to 2, the number of states as you want. And let me consider m equals to 1. So we are controlling our system of 2 states by just one control. And this system can be written like that. The YT, they are the element of the matrix A, and this is the control, plus initial conditions. We can see that this condition here is necessary for the controllability. Why that? Because if this this component equals to 0, then here we will obtain that, this equation, and then the control U, we control Y2, and Y2, it cannot control the Y1. The Y1 is, we can solve it explicitly. This gives Y1 equal exponential T Y1, Y1 0. There is no control here, and therefore this equation is free. We cannot control this equation. It cannot never control it, and therefore this necessary condition for the controllability. So what is about the sufficient condition? Is this system is controllable if A12 is different from 0? The answer of this question is yes. And this has been answered by Kalman and his collaborators in '69. And they gave a sufficient and necessary condition for the controllability of such systems. So system S is controllable at any time t, it doesn't depend on time, the control time, if and only if the rank of this matrix, or the Kalman matrix here, equals to n. So this B, the matrix control, then I will compute AB, A squared B, etc. till A to the power of n minus 1B. This must, the rank of this matrix equals to n. Just a remark, the size of this matrix is n times n times n. I mean that we have n columns or rows times, sorry, it's inverse here. We have n lines and n rows. Okay, let us go back to the example and let's apply this criteria of Kalman. In our case, the A is given by this matrix, the B is the vector 0, 1, and we have just the n in this case equal to 2. So we stop at n equals to 1. And the matrix of Kalman is given by this is B, and this AB. Okay, this, if we compute AB, we obtain this rows, and this is the B, and this AB has full rank if and only if A12, this component of matrix, of the coupling matrix called, doesn't different from 0. And this shows that the control travels, we'll go to the back, sorry, what is the wise? Okay. And this shows for the finite dimensional systems, the control travels along components. That means that I control Y2 and the Y2 control Y1 without any additional assumption. Okay, so what is the idea of the proof of Kalman criterion? As we have seen, the controllability equation is equivalent to prove that this operator is onto or is surjective. And in finite dimensional case, we know that LT is surjective if and only if its adjoint is injective. That means that if we can prove that the kernel of the adjoint of LT is reduced to 0, then the 0 orthogonal is exactly the n. And we are done here. Simple interpretations, we can compute the adjoint. Sorry, this x is which is missing here. So the adjoint of this LT operator is exactly, it takes some x from ln, and it gives us this operator LT adjoint. And the idea is to proceed from this formula here to prove that the kernel of this operator is exactly the kernel of the adjoint of the Kalman matrix. Intuitively, we can prove it, or we can see that if we expand this exponential of matrix, for instance, we can take B star, and this exponential, I will expand it in Taylor series. This gives A identity plus A star plus A star over n factorial, etc. And if I apply B, then we will obtain B star plus B star A star, etc. And this gives actually an intuitive proof of this Kalman criterion. I will not get into the details, but it can be proved like that, this way. Okay, so I will conclude this first part by some remarks. The Kalman criterion doesn't depend on the control time. So for finite dimensional systems, I can always prove that the Kalman condition is a sufficient condition at any time, and I can steer the initial state to the target state at any time. You can choose any target state and any initial state at any time. I can control our system as long as Kalman condition is satisfied. And second remark is, as we have seen, I used the fact that the kernel, orthogonal of the kernel, or the fact that LT is onto F under the F, its adjoint is injective. And this is not general is not true in general. For instance, in infinite dimensional spaces, it is not true. We will see that the difference between finite and infinite dimensional systems. And we can proceed in the same way for A, depends on time. In this time, the operator or the input of operator LTU is given in function of the relevant matrix. That is T0 here, we have T0 here, and B U as DS. And there is a criterion similar to the Kalman criterion for this non-autonomous system. It's called the Silverman-Misdale criterion. Okay, it is the Kalman condition is just a particular case of this Silverman-Misdale condition. Okay, now I will move to the most interesting case to us. It is controllability of linear PDEs. And to make things clear, or to make the differences more clear, I will start by this toy example. Okay, so I will let T be the control time, and I will consider this boundary controllability problem for 1D transport equation. Okay, so this is the most simplest PDE in the world. So this is the derivative with respect to T plus the derivative with respect to X equals to 0. And I will apply or exercise a control on the boundary and the X equals to 0. And it is just the initial state. That means that if we draw graph here, this one, there is 0, and I will call that the t-axis, and this is the x-axis. So the solution is given by the method of characteristics. This is the region of the control, or the control act. This x equal to 0, and we hope that this control acting in this boundary can control the whole system. So by the characteristics method, we can prove that in this region here, this is the region of the influence of the initial state, and in all the rest of the region, it is the region of influence of the control. More precisely, I have this graph here. As I have said before, sorry, what is the black? Okay, there's the region of the initial state, and this is the region where the control acts. And you can observe that if the control time is less than 1, then it is impossible to control, our system is controllable, and we cannot achieve or reach any target state. Because if we fix some time, sorry, why is that? If we fix some time, let, for instance, consider this time, and I let yt of x defined from 0 to 1, this target state. And clearly, in this interval here, I have to assume something like, for instance, yt of x, it must be equal to y0 of something, x minus t, for instance. And this condition doesn't fulfill the controllability definition of our system. And therefore, our system is not controlled at all. But if we move our controllability time to the right, for instance, if the t is larger than 1, then I can choose any target state here or here or here in time, and we can prove that my system is always controllable, and the control is given by this expression here. We can just make some substitutions to get the control expression, and the control depends only on the target state in this case. Just a remark, I will go back. This control operator here, we can see it as the BU in the first case. Here is the Dirac mass at 0 of u tx, and this will exist in some sense. I'll explain this later. So the control operator here, or the matrix in the first case, finite dimensional case, is the Dirac mass, and it is an unbounded operator. To make the differences more clear, I will consider this in this case the distributed controllability of the same transport equation. Instead of letting the control in the boundary, I will let it in the domain. I will to mention that controlling all the states, for instance, if we control from 0 to 1, is not very interesting from to view, since it is always controllable. So we can prove that if we control and the whole interval on 0, 1, so our system is always controllable, and it is not preferable from point of view of applications, since we want to minimize the cost of the forces. This time, I will consider this distributed control system. It is the same equation, but this time with control localized in this region here. Okay, so the support of control is in AB. And I ask the same question. If I give a target state, yt, can I find the control such that my solution or the solution of the system DC equals to the target state at this time? We can also compute the solution, the exact solution of this control system DC exactly by the characteristics method, and it is given exactly by this formula. I will fix t less than 1. This is intuitive because the worst case is t equals to 1, so we have just to work between 0 and 1. The first part of this solution is defined in this region here. For instance, if we draw this t and this x, so this is the region of the influence of this part of the solution and this second part, exactly as for the boundary control case. And we can see that if the time of control time is less than 1 minus b, then the intersection of these two sets is void set, and that makes this integral 0, and we assume that y0 equals to yt, and therefore our system actually there is no control, and we cannot hope that our system is controllable, since we will assume that y0 equals to the target state, which is relating to the target and the initial state. Also, if we assume that the a is larger than 0, if a is larger than 0, then for x less than a, also this integral will be 0. And therefore, we will assume that ytx equals to 0, which is violating to the target state, which doesn't fulfill the definition of controllability. And so we have two necessary conditions. The first is one, a larger than 0, and the second, if the time of control is less than 1 minus b. And And now we see that the control region must be of the form 0b, so I equal to 0, and there is again a phenomena of a minimal time of control. So the main differences between the finite and infinite dimensional systems or control systems are in principle two. The first is minimum time of controllability. This not happens. This didn't happen for the finite dimensional case, at least for autonomous system. And there is some geometric constraints that we should respect to be able to control the system or the state. Okay, now let me build a general framework to the control theory in infinite dimension, exactly like for the finite dimensional case. I will consider always T to be the control time, and H is a Hilbert space. It's called state space, and U is the control space. It's where the control lives. And I consider this linear system, exactly like for this, exactly as in the finite dimensional case. This time A is, it can be bounded or a mod operator from H to H, and this B, I will assume that this B is a linear operator from U, the space of control, to this space, to adjoint the dual space with respect to the pivot space H, this dual of the adjoint, the domain of the adjoint. We could just let this H, and we are done. But this deals only with bounded linear operator. So the boundary control operator as doesn't be dealt with in the setting. So this is a more general assumption than being H here. And my assumptions are the following. I will assume that A generates a C0 swimming group and H. That means that the exponential of this operator exists in some sense. And I will assume also that my control, or the adjoint of the control operator, this is just the adjoint of LT in the previous slides, is bounded or a continuous operator from LT, 0T, U to H. And this gives sense, or this makes sense to the computation. Under these assumptions, I can prove that for any y0 in H and U in this space, in L to 0T in value U, there exists a unique weak solution to system S given in this space, is continuous in time in value to H. And it is given by the same Duhamel formula, and this always be the LT, infinite or infinite case. And as previously, the controllability at time T is equivalent to the surjectivity or to prove surjectivity of the operator LT. As we have seen, in finite dimensional case, we have used these facts to prove the Kalman condition. If H is infinite dimensional space, this is no longer true, and we have to add the closure of the range of LT in H. And this means that if we prove that LT, adjoint of LT is surjective, it doesn't mean that the range of the LT equals to H. And this is the main difference between finite and infinite dimensional systems in theory. This last fact motivates another definition of controllability, and we have to change the name of the first controllability that we have seen in finite dimensional case. So the first definition is the definition of exact controllability. That means that this system S is said to be exactly controllable now, and not only controllable if at time T, if for any y0, any initial state, and any target state in H, I can find control U such that my solution is exactly the target state. This is the same definition as for the finite dimensional case. But this time we have to distinguish between the two definitions. This is called now exactly controllable. And for second one, which is motivated by this fact here, it's called approximate controllability. So my system is said to be approximately controllable in time T, if for any epsilon and for any y0 yt, I can find or control U such that the distance between my solution and the target state is less than epsilon. For the finite dimensional case, if I start from y0, I can reach yt if such control exists. But now, for approximate controllability, I will impose that we can reach an open neighborhood, an arbitrary neighborhood of radius epsilon. And this is the difference between the two. We can observe also that this is just the definition of the density of this range of LT in H. It's clear that exact controllability implies approximate controllability. So if we can reach the target state YT, then we can reach any open neighborhood in this around this state. So in general, how we prove controllability or approximate controllability for infinite dimensional systems? For the approximate one, we have seen that we have just to make sure that the kernel of the adjoint of the adjoint operator equals to 0, and this means that, or this can be written as the following. This is just the LTU equals to 0. The adjoint, sorry, for any t implies that x equals to 0, and this means that the kernel of LT equals to 0. Sorry, I think that there is no orthogonal here. And this property is called by unique continuation property. If our operator or our observations equals to 0, that entails that the initial state, sorry, this V, it's missing it, this V, sorry. This means that the V equals to 0, and it's just the kernel of LT equals to 0, LT star. And for the exact controllability, we know from functional analysis that if we take an operator A, or let it E is better, L from E to F, these two Banach spaces, is onto if and only if its adjoint is bounded from below for any x in F star. And I have used this fact here. So LT is onto if and only if there exists such CT such that the norm of the LT adjoint in start is greater than CTV. Just definition or writing of controllability or the fact that the L is onto. That's all. And to be more precise, if we let ZT equals to this quantity here, the exponential of the adjoint of this operator by V, then we can see that ZT solves this equation. This is simple since we can differentiate Z, and this will gives I start Z. At the instant t equals to 0, V is the initial state. So the operator, the adjoint operator of control becomes B start with the adjoint of B Z. And therefore, we can formulate our definitions as the following. So our system is approximately controllable if and only if B start Z equals to 0 for any t, then the initial state equals to 0. And the exact controllability reads as the follow. There exists some t such that this observability inequality is satisfied. This Z is the solution of the system, and the V is the initial state. Why this is more simple? Because in general, we can multiply this system by some quantities and making some integration by parts until arriving here or here. There is no general method to prove these two properties, but there is some techniques in the literature. Okay, so let us go back now to our example. As we distributed the controllability for the transport equation, we have found two necessary conditions. The first is the time must be larger than 1 minus b, and the second one, the a must be 0. And let's prove now that these two conditions are sufficient also by proving the observability inequality for the system. In the abstract settings, the a in this case is the differential is the derivative operator, and our operator a has domain h1 such that d in 0 equals to 0. The space h will be L2. The space of operator of the control, sorry, will be L201 also. And the operator B is a continuous operator from L201 to itself. And the goal is to prove observability inequality in this setting. Okay, now we have to compute its adjoint. The adjoint of A, sorry, there is minus here, and there is no minus here. So the adjoint is the derivative operator. The domain will be v in h, such that v at 1 equals to 0, and the adjoint of b is itself. So the dual problem reads like that. So this is the dual problem, and the goal is to prove that the z b tilde, sorry, b tilde z dt is greater than c0. To proceed, we can compute this very simple system that can be solved by the characteristics method, and we can prove that the solution is given. Sorry, there is minus here. The solution is given by this formula. So we are in this region now. This one. This is the region of influence of the initial state, the 0 and 0 otherwise. And we can also see that the previous writing can be interpreted like that. So it is the integration over this set U, excuse me, such that E, it is this region here. This is the same region that I've chopped. And the goal is to prove that this inequality is satisfied. And we can make here some substitutions. For instance, we can assume that S equals x plus t and make some computations and to arrive to this formula. So now we have this initial state squared, and we have this quantity here. The goal is to prove that there exists some t such that this quantity is larger than the integral of the 0 squared, which is equivalent to assume or to prove or to make assumptions on AAB such that this quantity is strictly positive. And this condition actually is called, or it is known as the geometric control condition. It means that the lines of this form t, which goes to x minus t, this x is in the in 0,1 and the t in 0t, it must enter to the control region along characteristics. So if I take any characteristics of the domain, it must enter this or touch this control region at time t or at time before 1 minus p. And this assumption actually can be seen, or after this assumption, we can see that the necessary conditions are also sufficient one. And this was all for these models for the transport equation. Now I will give general results. I will end this talk, this first part of talk by these two results. I will talk first of all on the wave equation and the general setting if we let t larger than 0 always. And omega is some open in Ln, but we assume it and bounded as smooth boundary. And this control region will be a small omega, and assume that the measure of this small omega is larger than 0. And I consider this wave equation, this just the wave equation, and I will exercise a control in this region. So this omega, capital omega, and this is the control region, small omega. And we have to control all the wave equation from this region here, control region. And this question has been answered by Bardos and Lobo and Rauch in 92 under the assumption of GCC. Okay, so if we assume that the couple, I'll explain this later, the couple small omega t satisfy the geometric control condition, then for any y0, y1 initial states, and for any target state y0t, y1t in this energy space, this where we study the equation in general, then I can find a control U in this space such that my solution is exactly the target one. What I mean by the geometric control condition is exactly as for the transport equation, but it is more general. For instance, in this setting, we can see that the couple T omega satisfy the control, the geometric control condition. That means that if we take any point, and I will send array or characteristics. It's called B characteristics in this setting. Then after some reflections, according to the geometric optic laws, it must touch the contour region at time before at finite time t. For instance, if I take this point and I send array, then it will be reflected on the boundary and it will touch. And if I continue like that, we see that there is no other choice. All arrays will touch the contour region at finite time. And the contrary, in this setting, for instance, if we send some rays here, we see that these rays will be always chopped, and this go to the right and be reflected to the left, and etc. And it will stack these rays. And therefore, in this setting, the wave equation is not exactly controllable. And this assumption is necessary and sufficient for the controllability of such equation. I will finish by the first part, this first part of talk by the controllability of the heat equation. I will consider the same settings here, and I consider the controllability problem for the heat equation. So there is just one derivative with respect to time. And this was an open problem till the 95 and 96, where this question has been answered by both the Russian school and the French school. And they proved that for when y0 in this space, in L2 space, energy space, there exists U such that UTU y0 equals to 0. So the heat equation is not exactly controllable, but it is not controllable. We can reach the state 0 in any time, and there is no minimal time of control for the heat equation. We can see that the heat equation is not exactly controllable by a simple argument, by a very simple argument. If we take my omega, big omega or capital omega will be this domain, and the small omega will be showed in red, is omega. We know that without control, if we let this 0, then the semi-group of the heat equation is analytic. So all the solution here is analytic, except in this region where we have regularity L2. So our solution is analytic here, and we aim to this solution to be equals to the target state in L2, which is impossible. So analytic things doesn't equal to things in L2. And this shows that we cannot hope that the heat equation is controllable, is exactly controllable, but it is controllable to the states y equals to 0. Okay, so natural equation arise naturally. We have seen for PDEs for just one equation that there is some condition must be respected, have to be respected. For instance, the minimal time or geometric contrast, and you can make the same or we can make the same question for PDEs, but this time for systems. For instance, if we consider the heat equation or two heat equation or two wave equation, the first equation, for instance, plus let's make A1C, and the second one ZTT is wave equation plus another coefficient Y, and I put a control N1 equation. And so the question here is what about the assumptions of A1 and A2 such that these two wave equations are exactly controllable? And this is the subject of the second talk, of the second part of this talk. Thank you.